Welcome to statics. This is the second problem that I'm solving. I hope that you watched the first one first. This problem is also a beam that has a pin at A. This time the roller at B is not at the end of the beam, and there's a distributed load on the beam. So there's two things different relative to the earlier problem. First step, step one, is to find the external reactions on the beam. So that's what we need to do. And I have already begun by drawing a free body diagram of the beam over here. There are no horizontal forces. Therefore, AX is 0, and all normal forces in this beam will be 0, and I will not talk about them anymore. So we have this load from the 80 kilonewtons per meter. It's a 2 millimeter long segment, and so the area is 160 kilonewtons, and we can position that at a position of 5, which is 4 meters plus half of 2 out along the beam. So that 160 kilonewton is out there at 5 meters from the end of the beam. So now I can sum the moments at A, set them equal to 0. This is in order to find the external reactions. I find that this unknown value by times 4 is positive. I have a negative 160 times 5. When I solve for by is 160 times 5 divided by 4. This tells me that by is equal to 200 kilonewtons. Now, summing the forces in the y direction and setting them equal to 0, I have AY plus BY, which is 200, minus 160 is 0. So interestingly, right, AY has to be negative 40. So what does that mean? That means AY is keeping this whole beam, AY is pulling down, it's keeping the whole beam from rocking on the roller at B. AY is pulling down with a value of minus 40. So I am going to indicate this on this beam at this point by sketching it as it is. AY is equal to 40. It is pulling down. BY is positive 200 pushing up. So step one, find your external reactions. Step two, separate the beam into segments which are similar. And so I am seeing a segment 1 here that I will treat first, segment 1, and a segment 2 in here, which I will treat second. And so my strategy is that I'm going to cut this beam somewhere in the middle of region 1, and then after I do that, I'm going to cut the beam somewhere in the middle of region 2. So let's get started. All right, so the first thing I'm going to do is I'm going to tell my professor what I am doing. And so I am in region 1, which is between 0 and x and 4. And so speaking of x, I should define what x is. X increases going off in that direction. And so my cut is now being made between 0 and x and 4. So I should draw a free body diagram of that piece of that segment of the beam. And again, remember, we found AY was 40. I'm indicating it's signed by the arrowhead. I've cut the beam. Because I've cut the beam, I must indicate the internal forces, which are shear And we always, on the left-hand side of the beam, draw shear pointing down. There are internal moments present in the beam, or possibly present in the beam, and that's it. I have no load occurring between 0 and x. So let's also just write that x is going out to here. And so now it's actually kind of simple. You just sum the forces in the y direction and set them equal to 0 in order to find what shear is. So what do I have first? I have minus 40. And I draw in minus shear. The reason I do that is because shear is pointing down. So I indicate minus shear. I now solve for shear. And we see that shear is equal to minus 40. This is true in this segment of the beam. And so now I can sketch that over here on my sketch of what's going on in life over here. And so what I've just found is that shear is equal to minus 40 kilonewtons between 0 and 4. And so that makes sense, right? It makes sense because the reaction was minus 40 at that position. And so that's what the shear is between 0 and x and 4. So now we have to think about what the moment is. So just like we did with the forces, we're now going to sum the moments, and we are thinking about what this position on the beam is feeling. And so first of all, it's feeling this bending moment, which is present in the beam. That's what we're actually solving for. So when we sum the moments at the cut, we must include that. So we write down this unknown m. So what else is happening? Well, shear is going through that point, so it's not going to do anything, but this 40 is going to do something. It's going to cause a positive moment of 40 times the distance between it and the end of the beam, which is x. So I will have m plus 40x is equal to 0. So therefore, m is equal to minus 40x. So we should check, does dm dx equal shear? Well, yes, it does, right? dm dx, looking at this equation, is equal to minus 40. Minus 40 is what we found. And so that is true. That helps us know that we're in good shape. So m is equal to 40x. So at x equals 0, m is 0. At x equals 4 meters, m equals minus 160 kilonewton meters. So we can plot that now. Here we are, x equals 0, and then we end up with minus 160, let's call that minus 160 kilonewton meters at this point here. We see a negative slope because we have a negative shear. So that was segment 1. I'd like to now consider what's going on in segment 2 of the beam. That is, what's going on in this part of the beam, the region between 4 meters and 6 meters. So let's go ahead and get started on that. So now I'm in region 2. Four is less than x, which is less than 6 meters. And so we should draw a free body diagram of the beam. So we have 2 possible things to work on. We can work on the left-hand side of the beam, which has the 40 kilonewton load. At x equals 4, the distributed load begins. And we are cutting it at a position of x. Or we could look at the right-hand side of the beam. The right-hand side of the beam looked like actually, I'm going to make an amendment to the left-hand side of the beam. So we also have this by going on, right, that we have to take into account. We have by of 200 at x equals 4. So let's add that. So we have the 200, we have the 200 kilonewton reaction at by going on there. So the left-hand side of the beam has a shear, it has a moment. These are what we're trying to find. If we were to look at the right-hand side of the beam, we would do this. There's nothing else going on here. There's no load except for this distributed load. And the cut is at x. The total length of the beam is 6, right? So if that's x, this is 6. And so this length is 6 minus x. On the right-hand side of the beam, positive shear points up, and the bending moment goes like that. So you can solve this problem either by looking at the left-hand side, right, or by looking at the right-hand side. It doesn't matter. It doesn't matter what you do. I'm going to choose the right-hand side just because it's a tiny bit simpler. So the rest of my work is now going to focus on the right-hand side of this beam. That is to say, I'm focusing my effort on thinking about that. So I'm applying the equations of equilibrium to that segment. Okay? So in other words, I am thinking about something. This piece of the beam is in equilibrium, right? And therefore, the positive shear that I see, so I write plus V minus the area of that curve. So the height of that distributed load was 80 kilonewtons per meter. The distance that I multiply it by is 6 minus x, which I already explained. That distance is 6 minus x. Therefore, shear is equal to 80 times 6 minus x. At x equals 6, shear is 0. At x equals 4, shear is equal to 160. X equals 4, shear is equal to 160. So let's look at our diagram and make sure that that makes sense. So at x equals 6, this is what I'm saying, shear is 0, and at x equals 4, we have that shear is equal to 160, so that would be right here on the diagram. So you might at first say, wow, that's kind of a big chunk difference from 40, but let's remember what's going on at this exact position. At this exact position, a reactive load of 200 kilonewtons pushing up is happening. And let's check out this magnitude. This is equal to 160 plus 40, which is 200. And so the fact that it rises abruptly by 200 kilonewtons makes sense to us because of the fact that By is equal to 200 kilonewtons there. So this is my shear versus distance diagram, and we are done with that, and it makes sense. So let's go on and finish off what's going on in the moment part of the curve. So at the cut, we would like to consider what's going on right here. I'm on the right-hand side of this thing, and I'm trying to solve for m. So I sum the moments at the cut, right? And so I have this negative m. I write negative because it is going clockwise by convention, so I must write minus m here. All right, and so this load, right, its magnitude we already worked out. Its magnitude was 80 times 6 minus x. That's what its magnitude was. Where is it located relative to this cut? Well, it's located at 6 minus x divided by 2. So this segment length is 6 minus x over 2. That's the distance from the cut. So I'm going to have an 80 times 6 minus x. I'm going to have an 80 times a 6 minus x. Where is it located? It's located 6 minus x over 2 from that. So is it positive or negative relative to this? That is negative. It's causing a negative moment. And so therefore, m equals 80 times 6 minus x times 6 minus x over 2, which is the same as saying 40 times 6 minus x squared. Let's check. Let's check what dm dx is, right? So if m is equal to 40 times 6 minus x squared, the m dx will be 80 times 6 minus x. Is that what we found for shear? Sure enough, it is. So we feel reasonably confident about this value. At x equals 6, moment is 0. At x equals 4, moment is equal to, what do we get? 160. So we have actually, at x equals 2, if I drop the negative sign, let's be careful here. Dm dx is minus, wait a minute, what's going on? Shear is 80 times 6 minus x. And m is equal to minus 40. Here it is. I found it. So m is, here's where I drop my negative sign. I have to put a negative sign right here. M is equal to minus 80 times 6 minus x. We have a minus sign here. Dm dx is minus 80 times 6 minus x times minus 1, which is positive 80. So I had a double mistake going on here. And so this is still true. And now I'm looking back over here. At x equals 6, moment is 0. At x equals 4, moment is minus 160. So what just happened in my head here was that I was looking back at this diagram and I was expecting to see some sort of continuity going on here. Why? Because there's no applied moment going on there. And so I kind of genuinely expect the moment curve between 4 and 6 to begin at that minus 160. And so you can see how I caught the lapse of a negative sign in my own work by thinking about this continuity point. All right, so let's finish off this plot. We wind up going from minus 160 to 0 to close off this plot. And if you plot a few intermediate values, you'll see that it does something like that. And so the moment and shear curves look like this in summary. And so in closing, we did two new things. We started thinking about distributed loads and how they work. And the second thing we did was we no longer had a beam that was only supported at both ends, but we have the beam that's kind of hanging off the end. And so you can see what that does, right? It creates a pretty intense shear on that beam as it hangs off the end. And of course, as the beam provides no load at the end, there's no load at the end. There's no internal shear at the end. But immediately following that B, the shear is pretty high. All right, that's it.